For over a century, classical physics and general relativity have mapped the universe using a single foundational unit, the zero-dimensional event. It is the idealized here and now, a mathematical coordinate with no width, height, or duration. But as we move into quantum gravity and holography, this absolute localization breaks down. Physical data like entanglement entropy cannot be pinned to a single point. These properties are inherently non-local. They belong to extended regions of spacetime rather than isolated coordinates. This creates a structural conflict. Our most advanced quantum data no longer fits inside our traditional geometric container. The solution is a coordinate shift known as Causal Diamond Kinematic Space. This framework swaps the event for the region. Instead of using zero-dimensional points as the base of the geometry, it treats causally complete volumes as the fundamental indexed units. Derived from standard Lorentzian math applied to holographic non-locality and mapped into causal set theory. To accurately model the structure of quantum spacetime, we have to stop mapping points and start mapping regions. On a two-dimensional grid, we map space horizontally and time vertically, marking an earlier event P and later event Q. From P, we plot its chronological future. From Q, its chronological past. Their intersection defines a precise volumetric region known as a causal diamond. This specific shape is not an arbitrary spatial volume. It is defined purely by causal order, the physical limit of what can influence what. Because it is defined by light paths, the diamond is covariant. Its duration, spatial extent, and boundaries remain mathematically consistent regardless of an observer's frame of reference. Anchoring spacetime geometry to causal structure is a proven technique, detailed in the 1967 work of Roger Penrose and E.H. Cronheimer. The causal diamond provides an observer-independent container capable of holding extended physical mechanics. We can abstract this into a second model. The left is physical spacetime. The right is an auxiliary graph called kinematic space. An entire extended region in physical spacetime maps to exactly one coordinate point in the auxiliary space. The coordinates are entirely relational, determined by the two endpoints. As the interval widens, its representative point moves vertically up the kinematic graph. If we shift the interval sideways without changing size, the point translates horizontally. A complex, morphing region in physical reality is compressed into a single, clean trajectory across a mathematical landscape. This has direct applications in holography. On this circular boundary, a specific interval anchors a geodesic arc that dips into the bulk space. Following the Ryu-Takayanagi principle, the length of that bulk geodesic is computed directly from the entanglement entropy of the boundary interval. That entanglement entropy cannot be assigned to an individual event. It is associated with the region as a whole. Mapping this non-local region to a single coordinate in kinematic space organizes that regional data into a point-like format. This framework allowed researchers like Jan de Boer and Robert Myers to analyze quantum observables known as OPE blocks and smeared operators. In standard spacetime, these perturbations behave as complex, non-local fields spread across the entire volume of a causal diamond. However, within the kinematic space of those causal diamonds, these smeared operators follow simple wave equations. Treating regions as coordinates relocalizes these quantum mechanics, providing the specific geometry needed to calculate them. We can extend this logic to causal set theory, which hypothesizes that spacetime is granular rather than smooth. A causal set is a locally finite, partially ordered set of discrete events. In this network, selecting a lower node X and upper node Y, the nodes ordered between them form a finite order interval. Counting these elements provides a direct proxy for the continuum volume of the spacetime region. Because the causal diamond is defined by order rather than volume, the geometric logic remains consistent, whether we are modeling smooth relativity or discrete mathematics. The causal diamond serves as a shared structural unit that functions identically in smooth relativity and discrete quantum gravity. The current literature supports a mature kinematic space in continuum holography and finite order intervals in discrete causal sets. We also have sequential growth dynamics. stochastic rules that build causal sets event by event. But this highlights a gap. There is currently no established dynamic theory governing the space of the intervals itself within a growing discrete set. Solving this requires defining new topologies, metrics, and transition rules specifically for the interval space rather than the event space. This frontier is accessible only by completing the shift in perspective, moving away from the point and toward the region. By redefining our basic coordinate as a causally complete region, we establish the mathematical requirements to connect entanglement, relativity, and discrete space.